Welcome students to the session on applications of Lagrange's equation. Part 2. We already learned two applications of Lagrange's equation in the previous module. Okay. Today we are going to learn a few more applications. A bead on a uniform rotating wire. You consider a bead on a wire OB, which is fixed at the point O and free to rotate in about an axis perpendicular to the plane with a constant angular velocity omega. Okay, so this wire, it is rotating with an angular velocity omega, and r is the distance of the bead from the point O at the time at a time t. Then angular velocity omega is d theta divided by dt, that is represented as theta dot. Okay, so here the constraint is that angular velocity is constant. Now if the particle is at the position B, then the distance is r, and we can split them into coordinate as x coordinate and y coordinate. X coordinate is equal to r cos omega t, because theta or omega is equal to theta divided by t, or theta is omega t. Okay, and similarly y equal to r sin omega t. Now we have to find, our aim is to solve this using Lagrange's function, and we know that Lagrange's function represents L equal to T minus V. T stands for kinetic energy and V stands for potential energy. So first of all we have to find the expressions for kinetic energy and potential energy. Okay, now kinetic energy is half mv square, but V is dx by dt along the x-axis and dy by dt along the y-axis. That is why here you can see that kinetic energy T is written as half m x dot square plus y dot square. X dot is velocity along x-axis, y dot is velocity component along the y-axis. So half mv square is in total. Okay, so we have to find x dot and y dot now. How do you find x dot? We know that x is equal to r cos omega t. So what is x dot? X dot is equal to r dot. This is like a product rule, so x equal to u times v. So we are applying the rule for differentiation for the product. So x dot equal to r dot cos omega t minus comes from cos omega t, differential is minus sin omega, that is why minus r sin omega t times omega. So I am writing the omega here. So this is x dot. X dot equal to r dot cos omega t minus r omega sin omega t. We are differentiating x with respect to t. So first we differentiate r, that is why it is r dot. Then we differentiate cos omega t, that is minus sin omega t times omega. So you can see that expression here. In the same way you differentiate y. So when you differentiate y, what is y? Y is equal to r sin omega t. So differentiate y, you will get y dot is equal to r sin omega t. So that will be r dot sin omega t plus r, the differential of sin omega t is cos omega t, times omega also will come. So that is r dot sin omega t plus so y dot equal to r dot sin omega t plus r omega cos omega t. So we got the expression for x dot and y dot, that is actually it is v x and v y, dx by dt and dy by dt. It is written as x dot and y dot. Okay, I hope the differentiation part is clear now. Now we have to find the kinetic energy. So before that, we have to find x dot in the expression for kinetic energy. Okay, the expression for kinetic energy, half mv square is there. That is T equal to half mv square. Here it is the sum of x component plus y component. So half m x dot square plus y dot square. That is the total kinetic energy. That is this expression. So we have to find x dot square plus y dot square. How do you find that? Okay, you can see here x dot square plus y dot square. Substitute for x dot and expand it. You will get x dot is r dot cos omega t minus r omega sin omega t. Expanding, it is r dot square cos square omega t plus r square omega square sin square omega t minus 2 r dot r omega sin omega t cos omega t. In the same way, substitute for y dot and square it, it will become r dot square sin square omega t plus r square omega square cos square omega t plus 2 r dot r omega sin omega t cos omega t. You can see that 1 minus 2 r dot r omega sin omega t cos omega t, and there is a plus 2 r dot r omega sin omega t cos omega t. They cancel each other, and the remaining terms are clubbed together. So r dot square cos square omega t is here, and there is one r dot square sin square omega t is here. So r dot square is taken as a common factor, and cos square omega t plus sin square omega t remains. And there is one r square omega square sin square omega t and r square omega square cos square omega t. So club these two terms by taking the r square omega square outside and into sin square omega t plus cos square omega t. But what is sin square omega t plus cos square omega t this term? That is equal to 1. Similarly here sin square omega t plus cos square omega t, that's also equal to 1. So what is remaining is x dot square plus y dot square is equal to r dot square plus r square omega square. That is the only term that remains there. Okay. So this is again we are now we are going to substitute this expression for x dot square plus y dot square into the expression for kinetic energy. So kinetic energy T is equal to half m times r dot square plus r square omega square. R dot square plus r square omega square is the expression for kinetic energy. So this is that one. Now we have to find the expression for potential energy. Now we know that the wire is rotating uniformly in a force-free space, and we can consider the potential energy there as 0. Okay, it is moving in a force-free region. Okay, so we can the potential energy of that object is 0. Now taking the Lagrange equation, L equal to T minus V, that is purely become kinetic energy. So L equal to half m times r dot square plus r square omega square. Now we know that the Lagrange equation say d by dt of dou L by dou t, I mean dou L by dou x dot. Here okay, dou L by dou x dot minus dou L by dou x equal to 0. This is a Lagrange equation. Substitute the expression for L in this. So what will be that answer? Now first of all we have to find here what is x actually. Is omega, the position vector. So in this case we can rearrange into this will be r dot. Okay, I mean r. So the Lagrange equation d by dt of dou L by dou r dot minus dou L by dou r equal to 0. So substituting the first bracket term dou L by dou r dot, that means you have to differentiate the Lagrange with respect to r dot. So when you differentiate with respect to r dot, only the first term remains, that is L half m times r dot square, that become 2 r dot. So half cancel, so that will give m r dot for the first bracket. So d by dt of m r dot minus second is dou L by dou r, that means differentiate L with respect to r is the second term, so r square here. So half m times r square omega square, so it becomes 2r omega square, and 2 and 2 cancels, that will be mr omega square. So minus mr omega square equal to 0. Now the first term you have to differentiate with respect to time. So it will become mr dot d by dt. So it will become mr double dot minus mr omega square equal to 0. Rearrange and take m outside and cancels. So you will get r double dot equal to m r omega square. R double dot is acceleration. I'm sorry, there is no m there. M cancels. Okay, r double dot equal to r omega square. That is acceleration equal to r omega square, the object moving on a circular track. So we used Lagrange's equation for finding the expression for the acceleration of the bead moving on a circular track or on a circular the movement which is moving along the uniform circular motion. Okay. Okay, students, as the next example, we can consider a one-dimensional harmonic oscillator. For example, a mass attached to the end of a string whose other end is fixed to some wall or something like that. And if the spring is displaced from its equilibrium position and released, we know that the spring executes harmonic oscillations. Okay, so here we have to find the expressions using Lagrange's equation for that. So we are familiar with this harmonic oscillator, and we describe the example of harmonic oscillator also. Any oscillators. Okay. So you consider, or suppose the spring system that we considered as example move along the straight line back and forth a number of times. And you know that it has got kinetic energy and potential energy. When you stretch that to the extreme position, it has got maximum potential energy. When you leave it, the potential energy decreases and kinetic energy increases. When it reaches equilibrium position, its energy will become completely kinetic and zero potential. And due to this kinetic energy, what happens? It moves to the other extreme position. So in that way, it oscillates. So what is the expression for its kinetic energy and potential energy? Because our aim is to solve this one-dimensional harmonic oscillation using Lagrangian formulation. Lagrangian formulation consists of L equal to T minus V. What is T? T is the kinetic energy and V is the potential energy. And what is the expression for kinetic energy? That is half mv square. So half m x dot square. X dot stands for velocity. In the same way, the potential energy of a spring, you all learned that half k x square, where k is the spring constant of the spring. Okay. Now, what is L? L equal to half m x dot square minus half k x square. Now we have to apply this in Lagrange's equation. What is Lagrange's equation? D by dt of dou L by dou x dot minus dou L by dou x equal to 0. So we need dou L by dou x. So d by dt of. So the first bracketed term, dou L by dou x dot. So you have to differentiate L with respect to x dot. So when differentiating L with respect to x dot, here the first term consists of x dot, second term no x dot there. So you have to differentiate first term only with respect to x dot. So when you differentiate this, half m is constant. Differential of x dot square is 2x dot. Okay, so 2 and 2 cancels. And it gives m x dot minus. Then the next term is dou L by dou x. That means you have to differentiate L with respect to x. So differentiating x is in the second term here. First term consists of x dot. So we are now we are differentiating with respect to x. So you have to do the differentiation only for second term. So dou L by dou x is half k times x dot square. What is the differential of x dot square? It is 2x. So 2 and 2 cancel. So the answer will be kx. Okay. So this is kx equal to 0. Now again you have to differentiate because there is a d by dt of mx dot. That will be mx double dot minus kx equal to 0. One more thing is there. I think okay, potential energy is given by the expression for second derivative. The second derivative is dou L by dou x, but L is mx dot square minus half kx square. So there will be one extra negative here. So that this become positive. Okay, because it is half mx dot square minus half kx square. Okay. Now that is mx dot plus kx equal to 0. or what is mx dot? It is like ma, because x dot is velocity. One more differential means it is acceleration, plus kx equal to 0. Or you can say it is f plus kx equal to 0, or f equal to minus kx. This is the force law for an oscillator, a force law for a movement of a spring, or it's also known as Hooke's law. So we derived the expression for force or acceleration for a harmonic oscillator using the method of Lagrange's formulation. Okay, students, as a next application, let us consider a particle moving under central force. Central force, like for example, an object moving under gravity force or such a force. Okay, a particle moving under central force. So here, which are the generalized coordinates in this case? Here are the distance from the center of movement and then the angle. These two are the generalized coordinates. That is, r and theta are the generalized coordinates here. Okay. So two generalized coordinates. One is r, the next is theta. So I think till now we learned about systems or situations in which one generalized coordinate. Here we have two generalized coordinate. Okay, for an object moving under central force. So r and theta are the generalized coordinate. So as we know, we have to solve this situation. For that we have to set up the Lagrangian. What is the Lagrangian? L equal to T minus V. T stands for kinetic energy and V stands for its potential energy. So how do you find the expression for potential energy and kinetic energy? That's the question. So T equal to half mv square. We already derived this in the case of the bead at the bead on the rotating string. In the so the same expression we are using here also. Okay. You can refer that derivation part. So half times m r dot square plus r square theta dot square is the expression for its kinetic energy. And potential energy in this case it varies with it depends on the position r, at whatever the position of r. Now L, what is L now? L equal to half m times r dot square plus r square theta dot square minus v of r. The derivation of potential energy is same as that of the case we detailed earlier in the case of the bead on a string. Okay, the same you can apply here also. Here potential depends on r. In that case we took potential as 0 because the r is a fixed thing there. R is okay. R was the only generalized coordinate there. Here it is not like that. In that case r was fixed. Here it is not like that. R and theta, there are two generalized coordinates here. So now for applying into Lagrange's equation, we need to find dou L by dou x dot and dou L by dou x. So Lagrange's equation states d by dt of dou L by dou x dot minus dou L by dou x equal to 0. But here there are two x's. One, the generalized coordinate. One is r, another is theta. So you have to find expressions for these two. So you have to find dou L by dou r, dou L by dou theta. Then you have to find dou L by dou r dot, dou L by dou theta dot. Okay, so 4 steps. Till now we learned situations which only one generalized coordinate. Here there are two generalized coordinates. That is why this 4 section calculation will be there. Now we will go to the calculation part of this. Okay. So first of all we have to calculate the value of what? Dou L by dou r. What is L here? And okay, you can see dou L by dou r. Dou L by dou r. You can see that r is here in the second term. not in the first term, not in the last term. Okay. So what is this term? Yeah, r is there in the second term, and r is there. V potential is also a function of r. So when you differentiate dou L with respect to r, the second term you have to differentiate, and the third term you have to differentiate. So that will give half m r square. When you differentiate, it becomes 2r theta dot. So 2r theta dot square minus again dou v by dou r. This 2 cancels. So this gives m r theta dot square minus dou v by dou r. Okay. So hence we got the expression for dou L by dou r. The same way, dou L by dou r dot. Okay. Dou L by dou r dot. So you have to differentiate with respect to r dot. When you see the expression for Lagrange and L, the first term includes r dot. Second term there is only r, and third term is also dependent on the function of r only. So differentiate only first term, because here differentiation is with respect to r dot. So half m times d by dt of r dot square. So it will become 2 r dot, and 2 and 2 cancel. So you will get m r dot as the expression for dou L by dou r dot. Dou L by dou r dot is equal to m r dot. Okay. Now we have to find the same for theta, dou L by dou theta and dou L by dou theta dot. Okay. So dou L by dou theta. Let us see in the term for in the expression for L, is there any thetas there? No. The first term is r dot term, second term is r and theta dot, and third term is a function of r. So there is no term including theta. Therefore, when you differentiate dou L by dou theta, L with respect to theta, you will get an answer 0. Next, you have to differentiate dou L by dou theta dot. That is equal to when you differentiate theta dot. Theta dot is included in the second term only. So you differentiate, it will become half m times r square theta dot square. So d by d theta dot of r theta dot square become 2 theta dot. So this will be half m, then r square 2 theta dot. This 2 cancels. So this will give m r square theta dot. So you can see that here 2 generalized coordinates. So we have to find dou L by the expression for the Lagrange equation. We know the Lagrange equation is d by dt of dou L by dou x dot minus dou L by dou x equal to 0. But here there are 2 generalized coordinates r and theta. Therefore, this equation there are 2 Lagrange equations, one in terms of r, another in terms of theta. So d by dt of dou L by dou r dot minus dou L by dou r equal to 0. There is one expression. Similarly, d by dt of dou L by dou theta dot minus dou L by dou theta equal to 0. So 2 Lagrange equations are there. So we can write these 2 Lagrange equations now. What is that? First one, d by dt of dou L by dou theta, dou r dot. First we will write r. Dou r dot minus dou L by dou r equal to 0. This is the first one. And the second one is d by dt of dou L by dou theta dot minus dou L by dou theta equal to 0. What is dou L by dou r dot? This is m r dot. Okay, so we can substitute m r dot minus dou v by dou r minus dou v by dou r, then minus dou L by dou r. What is dou L by I think I made a small error here. Just a minute. Okay, so this will be d by dt of dou L by dou r dot, that is m r dot minus dou L by dou r. Dou L by dou r is m r theta dot, minus of minus will become plus. Okay, dou v by dou r. equal to 0. Okay. Yeah. Again differentiating that with respect to t, because d by dt is there. So this will become m r double dot minus m r theta dot square equal to minus dou v by dou r, which is the expression for force in the case of central force. Okay, this is m r double dot. I will replace it m r double dot. So so we got the expression for force in the central force problem. So we know that for central force problems the force is given by minus dou v by dou r. So that we got here minus dou v by dou r is equal to mr double dot. Mr double dot is the acceleration. I mean mr double dot is a force. R double dot is the acceleration. So force is equal to minus dou v by dou t. Okay. And considering the next Lagrangian, that is Lagrange equation, that is d by dt of dou L by dou theta dot minus dou L by dou theta equal to 0, we can substitute dou L by dou theta dot. What is dou L by dou? Okay, that is mr square. We already derived that dou L by dou theta dot is equal to mr square theta dot. Okay, so this will become d by dt of mr square theta dot, mr square theta dot. Okay, then minus dou L by dou theta is 0 equal to 0. Dou L by dou theta, we got expression as 0 here. We derived that earlier. Okay. Now this again differentiating mr square theta double dot equal to 0. What is theta double dot? It is omega. So it is m omega r square. M omega, or you can write it as, wait just a minute. This says that d by dt of m r square theta dot is equal to 0. What is m r square theta dot? Theta dot is omega. So m r square omega is actually. So what is m r square theta dot? Theta dot is omega. So it is m r square omega. But r omega is v. So it is mvr. It is L, angular momentum. So this says that d by dt of L, the angular momentum, is equal to 0. So derivative of angular momentum is 0. That shows that angular momentum is a constant. It's a result here. So L equal to 0. The angular momentum, L is equal to constant. L equal to constant. Okay, so that is the case of motion under central force. The angular momentum is constant. So we derived that also using Lagrange's equation. Okay, only in this derivation we used two separate generalized coordinates, and therefore we used two Lagrange's equations, one with respect to r generalized coordinate, another one with respect to theta. The rest everything is same. Okay students, thank you. Okay students, another application of Lagrange's equation is for LC circuit, an electrical circuit with an inductor and a capacitor. Okay, so the charge on the capacitor Q, let Q be the charge on the capacitor after it is completely charged, and during discharge what happens, it sent current through the inductor, and the inductor stores energy in the form of or magnetic energy. What is the expression for magnetic energy in the inductor? It is half L I square. Half Li square is expression for energy in the magnetic field of inductor. In the same way, what's the expression for energy in the capacitor? That is half Q square divided by C. So here the Lagrangian L is given by, instead of T minus V is the expression, but here T is the magnetic energy stored and V is the electrical potential energy stored. So you can write it as half Li square minus half Q square divided by C. Okay, here we can consider Q, the charge, as a generalized coordinate. So what is actually this I? Current I is dq divided by dt. That is it is Q dot. So you can write Lagrangian as half L Q dot square minus half Q square divided by C. Now, in order to solve the Lagrange equation, we need dou L by dou Q dot and dou L by dou Q. Here Q is the generalized coordinate. So differentiating L with respect to Q dot, only the first term consists of Q dot. So this becomes L Q dot. Differentiating second term with respect to Q, I mean first term is only Q dot term, so no need to differentiate that, only the second term. So half Q divided by C. This become half Q by C because Q square differential is 2Q and 2 and 2 cancel. So half Q by C. Now applying this in the Lagrange equation, what is that? D by dt of dou L by dou Q dot minus dou L by dou Q is equal to 0. Substitute d by dt of dou L by dou Q dot is L Q dot minus of minus Q by C equal to 0. And this gives L Q dot, again you have to differentiate because d by dt is there. So this is L Q double dot minus positive Q divided by C equal to 0. And rearranging Q double dot plus 1 divided by LC Q equal to 0. So this is the equation for the differential equation for the an oscillator and LC circuit. Q square by Q double dot d square Q by dt square plus we know the expression for LC circuit, d square Q divided by dt square plus omega square Q equal to 0. This was the expression we learned in and derived the other way. So you got exactly the same equation here also. So here instead of omega square, you can see that it is 1 divided by LC. So what is omega? That is 1 divided by root of LC. And what is omega is actually 2 pi times the frequency nu. That is 1 divided by root of LC. So what is the expression for frequency? Nu. Frequency nu is equal to 1 divided by 2 pi root of LC. So we derive the expression for a differential equation for the LC circuit and the frequency using the concept of Lagrange's equations. Okay. Okay, students. Thank you.